So today I'm going to be talking about my presentation. Going to be about exploring effect of freight and emergency vehicles on distribution factors of concrete T-beam bridges using refined analysis and machine learning. So we all know that the actual current load rating practices, they provide safe load carrying capacity for service bridges, and they provide the basis for evaluation, which is like this equation shown here. And they actually support permit and posting decision. And the rating is actually defined by the actual MB in terms of tonnage and rating factors. So concerns that are actually known within the bridge community are existing damage and deteriorating condition on surface bridges, ever increasing demands for transporting goods and services. Track size and weight continue to grow and exceed legal limit, and reliability of unserviced structures under the passage of irregular loading scenario. So there are some news that actually the FHW has given in 2013. So the Federal Highway Administration ordered all the states to rate their bridges within their state inventory for a class of vehicle called the HSVs, which are the specialized hauling vehicles by the end of 2018 for Group 1 bridges, and which are the shortest bridge spans that are under 200 feet. And by the end of um, 2022 for Group 2 bridges, which are those bridges that are not included in Group 1. So you can see the SUs that we have in the database. So these are this is the SU 4, 5, 6, and 7 with the axle loading 4, 5, 6, 7 respectively. So challenges has gotten a little bit bigger since the mandate has been declared. So the U.S. bridge inventory will be impacted by this new regulation imposed by the Federal Highway Administration, and this results in a need to post these structures for HSVs loading. Approaches to face these challenges could be like applying weight restriction and providing secondary route, which will actually would slow down probably like the transportation, which is something that we wouldn't like to have. So more rational approach includes a better understanding of our structural system behavior, which are redundancy, load distribution, impact, and damage. Now, where we can make load rating improvement, looking at this picture here, these equations. So this figure provides a breakdown of the various components that are used to arrive at the rating factor for a given bridge. This rating factor represents the fraction of additional live load capacity remaining above the target live load when removing the effect of dead load. So improvement can be done either looking at this equation, um, we can actually increase the resistance to have the rating factor being boosted a little bit, or we can try to understand like the system factors on improvement, or the improvement in understanding of loading effect, which are those one that are used mostly in the denominator. If you can look at it, we have here the GL, the impact factors, and the load effect. So, but how do we overcome this problem of low rating? So either we can use, well, the method that we can use is method of refined analysis. So which is inherent structural redundancy due to complex interaction and simplified increment design and rating practices. So application of component-based approach. So having here a whole structure and ignore the whole system level behavior and deal just with the individual component. So now our focus is going to be where we can improve what, as we talked in the previous slide, what we can improve, what we can focus on to improve the rating factor. So in here, we can actually take the G, which is the distribution factors, and as you can see, the equation of it is presented below. So refined method of analysis. As shown, allows for alternative methods of analysis which satisfies equilibrium, compatibility, and material properties, and more rigorous and accurate analysis include Grolage method, finite element method, finite difference method, and finite strict method. So having a structural system here, you can either use one of those. But in our focus here, we're going to be using the finite element analysis of 2D. So for the research objective we have here, the first objective would be to predict the change in distribution factors using the refined analysis method. So those include the 4 steps that we have here. So the first one will be identifying the bridges with the rating factor that are between having rating factor between 0.7 and 1 from the database. And the next one will be like refined analysis of bridges and doing the refined analysis of those bridges and the determination, determining like the distribution factors, as you can see here from the flow chart. So this is what we do in order to reach to that point, and then comparing the actual LRFD specification distribution change. So we actually gonna try also to do a parametric analysis in order to predict the change in these distribution factors. That is going to be like distribution factors obtained from the H2 and the refined analysis method. So the second objective would be to actually classify the track that govern for the distribution factors. So as you can see, the steps that are actually used is going to be like getting the bridge population, selecting the bridge population, doing the refined analysis and getting the distribution factors. The next would be to identify the track type that govern in terms of critical distribution factors. And then we populate our database, as you can see in the flow chart here. And going to the next thing will be doing a parametric analysis again using a classification algorithm called the supervector machine in order to classify those tracks that actually govern for the distribution factors. So the methodology will include, as we said, from those objectives, the bridge selection. So for the bridge selection, we're going to be focusing on those bridges that have the rating factor between 0.7 and 1, and to explore the potential of increasing the rating factors. And all of them are actually T-beam bridges, and they're really important since they represent 23% of the girder type bridges in the state of Virginia. So the methodology will include developing a method hierarchy, so which is reduced refinement 2D structural analysis using LARSA 2D or 4D, and then the modeling approach would include like would be a bridge that was selected from the literature from this study, Harris et al. 2020 for ground truth of model, and then we're going to compare. Actually like we're gonna take they tested actually the bridges in the field, and then from the refined analysis that we're gonna develop for that bridges, we're gonna try to do the validation based on that bridge. So you can see here we have the 2D plate, which is the which is the model that we have created for the particular bridge, and then we try to validate it with the field testing from the literature. This is actually a picture from that study for the bridges that have been tested. So again, once the validation is made, now knowing like the route of making those models, so now we are gonna start after, and we already actually selected those bridges that are gonna be selected for these studies. So we will start the modeling process. For the modeling process, what we do going to be based on the validation, on the result from the validation, and after that, for the live loading, we're going to be using this track, the track list that we have provided here. So which is tandem, HS20, and the SUs that we just talked about at the beginning. And now from there, we're going to determine the load effect. So you can see like also for the loading scenario, we had the track position. We selected like once you get like the worst spot where the bridges can get the highest load effect, we actually like try also to position the track in a transverse direction, and that included 1 lane and 2 lane, like 2 track or 1 track. So going to the next, the results show that once we created this model and populate our database, we have we came up with these equations that are shown here. This is for the moment, and the shear you can see here, and these are the loading, the loading, and here we have the R square, which we get from the statistical analysis that we have implemented here, which is regression actually modeling. So here you can see here the R square that we have the list, it is actually 0.74, and so these are the equations that we obtained for the distribution change from this equation. Now, what we're going to show you next is how how much this equation can be like how much it validated this study. So here we have actually a representation of those of the equations, refined analysis, and the ASHTO. These are the 4 parameters model that have been developed versus the refined analysis model DF. So here we have the threshold that are shown actually as hidden lines, and these one are actually like the red dots actually show those bridges that when we use the normal distribution, like with the confidence interval, those bridges were the one that was out of boundary based on the normal distribution. So they were out of the confidence interval on 90%. So those bridges actually, as you can see, most of them, they were within the threshold that we have set. So this threshold is within 10% error. So those bridges, they are actually like could be validated using the equation, which shows like how much reliable this equation could be. And that has been shown everywhere here. You can see also most of the spot, those bridges that are actually out of boundary, also most of them, they could be validated by those equations. So from moment to shear. And for the classification, SVM, we have actually used support vector machine as our algorithm to classify those tracks that could be the governing tracks for the bridge population for this study, I mean. So you can see like 2 parameters were selected. These were the most 2 significant parameters that we could detect, and that was the span and the spacing that you have here on the Y and the X-axis respectively. So considering, for example, the moment for interior 1 lane, we have seen that 2 track could actually dominate, could actually govern for this. And you see for these regions that are shown in yellow here, we have the SU track, and the remaining one were the tandem that were actually governing. And here we have the HL9 tree, the HS20, and the tandem that were actually mostly governing for the case of interior moment. And moving on to the next, for the exterior, we have seen a variety, especially for the 2 lanes, we have seen a variety of track that actually govern for this loading case. So we have the HS20 and the SU4 actually, and the SU7, and most of them, they actually occupy almost the half of this region. And now here, considering the 1 lane interior again for shear, we mostly like we have the tandem that govern for this case, and so on. And here, especially for the exterior 2 lane shear, for the exterior case for shear 2 lane, we have all of those SUs actually got in the classification, and they mostly govern for this. So comparing the results that were obtained from the changing distribution factors in between the track, we have seen here the HS20 or tandem. This is now the values that we, this is showing like quantitatively showing like the comparison. So here we have in most of the cases, we have the HS20 or tandem compared to the SUs. So we have on the Y-axis like the change in distribution, and here are the bridges that we actually model. And so for those actually like for the markers that have been filled, those one are the one that governs, and the one that has been left void, and are those ones have a lower distribution factor compared to the one. So seeing here, having all of them mostly being filled with the red color shows that the HS20 or tandem are mostly governing for these cases, if you look at it. And but there is a problem here. Looking at the exterior 1 and 2 lane shear case, we have seen so many of the blue dot showing that the SUs are the one that govern this. And comparing them, you see that there is not much difference between the SUs and the HS20 or tandem tracks, change of distribution factors. However, in this case here, we could see like for some of them, there is a huge difference. So you see a big gap between the SUs and the HS20. So for the conclusion that we have drawn from this study, we see that the design track of tandem loading govern the computation of the critical moment and shear distribution factors for interior girders. However, for exterior girders, the SU track mostly lead to a high distribution factor, especially for two-lane loaded scenario. So the distribution factors actually computed for interior girder using the SU track in refined analysis are very close to those obtained from the design track on in tandem. And the SU tracks govern the computation of the distribution factor for exterior girder. Only SU track can be considered in refined analysis of configuration bridges to obtain the critical distribution factors. And given the geometrical characteristic, the developed models could predict the percent change in distribution factor with a coefficient of determination which is above 0.74. And considering the ability of the prediction equation in detecting percent change in distribution factors, this equation can be used as screening tool to make decision about whether refined analysis can improve rating factors for a particular bridge or not. So that was the end of my presentation. Thank you. If you have any question, I'll be pleased to answer them.
Thank you, Abdou. I appreciate that. That was an interesting presentation.